Let a and b be positive real numbers. If x squared plus y squared is less than or equal to 1, then the largest that ax plus by can equal is one of these values. Okay. So my first instinct here was to just use a Lagrange multiplier style optimization and go through all the computations. But I'm wondering if there's maybe some kind of other clever way that we could manipulate this. X squared plus y squared is less than or equal to 1. Then the largest that ax plus by can equal. Oh, so a and b are fixed, positive. I mean, process of elimination, we might be able to eliminate a lot of the answers here. So, just by choosing values of a and b, but I typically like to actually solve the problems full out rather than using the multiple choice answers as hints, basically. So, I mean, the one thing to realize is that the values of x and y which maximize ax plus by so x squared plus y squared is less than or equal to 1. The values of x and y which maximize this are going to be, they're going to satisfy x squared plus y squared equals 1. It's pretty easy to see that if x squared plus y squared is strictly less than 1, then we could increase either x or y, and that would increase this by some little amount. So I'm just going to replace this immediately with x squared plus y squared is equal to 1. I mean, I suppose there might be some geometric way of doing this. If I say, for example, ax plus by is equal to some constant c, I can move that constant c. Imagine, for every different value of c, this gives us a line in the plane. And because x and y are positive, I mean, this translates to by is equal to c minus ax. So for every different, remember that a and b are fixed. Every different value of c is going to give us a line like this. And all of the lines will be parallel for different values of c. So for different values of c, we're just going to have a bunch of lines that go like this. And if you look at this version of the equation, remember that a and b are both positive. If I increase c, that means the lines are moving in that direction. Okay, so basically what I want to do is I want to move the lines in that direction as far as possible, such that there is still going to be intersection with that circle. So what I need to do now is draw a circle of radius 1. And it's pretty clear also that as I move these lines in that direction, the line that I'm looking for is going to be the one that's tangent to the circle. Okay, so what I've done now is I've reduced the problem to finding which of these lines, if I think of all of these as being different lines for different values of c, I'm looking for the one which is tangent to the circle. What might be the best way of doing that? Well, if I draw a line from the origin to that intersection point. That's going to intersect the line at a right angle. And that direction is, if I put a vector here, then V is equal to, is it AB or is it BA? The normal vector is going to be A, comma, B. Of course, this just gives us the magnitude of this. So the point right there if I find that point, it should give us what we want, right? And that point is, of course, going to be, because the vector which goes from the origin to here is of magnitude 1. If we call this point P, then P is equal to AB divided by A squared plus B squared under square root. Does that help? I mean, it gives us one point that's on that line. So now we can easily solve for C. C is equal to AX plus BY, where the X coordinate is this, it's A divided by that magnitude, and the Y coordinate is B divided by that magnitude. So this becomes A squared over root A squared plus B squared plus B squared over root A squared plus B squared. So C is equal to A squared plus B squared divided by the square root of A squared plus B squared. And so C is equal to A squared plus B squared. And that is one of the answers, I believe. Yeah, that's option. Oh, nice. I've called this constant C, and that also happens to be the option which is correct. Yeah, so essentially what I have done here actually is argued through the whole idea behind Lagrange multipliers. I'm not going to go into the details of how Lagrange multipliers work exactly, but the idea of taking these straight lines and parameterizing them by C, and then realizing that as C changes, we shift these lines in that direction, and then we're looking for the line which is tangent to the circle. And then I've translated it into a geometry problem, essentially. If we find that point right there, that point is, of course, on the line and on the circle. So the fact that it's on the circle means we can find the coordinates very easily. And the fact that it's on the line means that when we substitute this value of x and this value of y into here, that gives us the maximum value of this quantity ax plus by. Yeah, so nice little problem. Not much more to say about it now, but thanks for watching.